Recording, rolling. It's Monday, January 12th. So I'm going to cover 7.3 with you guys today, special exponential functions, right, which a lot focuses on this character E. Should get a little bit on Friday, but more than that. Right? All right, but so let's start at the top. So, guys, over the weekend, I recorded the videos for 7.3, 7.4, 7.5, like the longer form videos that have lots of examples from the book. So, kind of look ahead and pace this week out if you like. Okay. The next Alex assignment has been open for a few days, so 7.4, 7.5, that's due this Friday. And this Friday, I will get you guys your Module 7 quiz. Okay, so you guys good with the agenda, what we're doing? Okay. All right, so what is it? Special exponential, right? So we're looking at this, we're going to have the base E, like right here. You guys see this base E? Right? So what is E? It's a number that's stored on the calculator. Right? So, guys, here's one way to find E. Guys, look real close at this, because this is kind of a funny thing. If I do 1 plus 1 over x and then raise that to the power of x, right? You guys see that? Right? Now, you can plug in whatever you want for x. Like, here, guys, how about this? What if you plug in 1 for x? What is 1 plus 1 over 1?
1, 2.
2. 1 plus 1 is 2. And if that's all raised to the power of 1, 2 to the 1 is 2. So that would be 2, right? Right? What about this? What if you made x... Here, I'm going to do this. 1 plus 1 over the answer, and then to the power of answer. Okay, so if I plug in 1, and then that takes the place of answer, then yeah, I get 2. You guys see that? Okay. Let's plug in, how about 10? So 10. Guys, 1 plus 1 over 10, is that like 1.1? Mm-hmm. Raised to the power of 10. That's like 1.1 multiplied by itself 10 times. So if I plug that in, okay. I get 2.59 something.
You only make it for a week.
Let's keep going. Guys, what if you plug in 100? 100.
Not that.
Okay. Guys, look here. Think about this. If I plug in 100, guys. 1 plus 1 over 100, is that just a tiny bit bigger than 1? It's like 1.01. And we're going to multiply it by itself effectively 100 times, like 1.01 times 1.01 times 1. So on. Okay. So if I plug that in, I get 2.77. Huh. So it looks like this is actually converging to some particular value. Do you guys see that? Okay. What if I plug in 1,000,000? Dude, guys, 10 to the 6. Could that be 1,000,000? That's 1,000,000, right? Okay. And I plug that in. Okay. 2.718 something. You guys see that? Okay. Yeah. Now, if you let x go all the way to infinity, you're making the number inside the parentheses get really, really close to 1, and you're blowing up the exponent to, of course, infinity. Right? Right. And then, guys, in a calculator, everybody do this in the calculator. Hit second. And you guys see this key that says ln? That stands for natural log. We'll talk about that in a few weeks. But right above it says e to the x. Now, if you hit second first, right, and then you hit that key, you get e to the something. Everybody should have that on their screen. Everybody's got that on the screen? E to the something? Type 1, because e to the power of 1 is just e, right? Right? Anything to the power of 1 is itself. Right? Hit enter, and oh, look at that. 2.71828, so on. Right? Now, that is actually an irrational number. That's to say that it goes on forever without any patterns. It does no repeating digits. Okay. But, okay, so what is this good for? What is this good for? Okay. Let me show you guys a couple of things that's really cool about this E character. Okay. First, if I graph very simply y equals e to the x, let's do that. Y-axis, x-axis. Let's do y equals e to the power of x. Okay. I mean, guys, this is exponential, isn't it? X is in the exponent. Right? It just has a very special base, e, which is, of course, approximately 2.71828, so on, Okay. Right, so let's do xy table. We'll throw a few points on here. Xy. Let's go x is -2, -1, 0, 1, 2. This should give us a pretty good table. Okay. Right, so what's e to the power of, let's start with 0. Right. What do you guys think? I don't even have to do the calculator for that. I bet you guys know exactly what this is.
0.
1. Aha.
What?
How about e to the power of 1? Well, actually, you just did that a minute ago. That's, of course, 2.718 something. I'll cut it off at some point. What is e squared? It's like 7.389 something. Okay. E to the -1. Is that the same thing as 1 over e? 1 over e, which is about 0.37 about. Okay. And then e to the -2, 0.1 something. Okay. Some of it, just a couple digits. Right, so put this all together. -2, -1, 0, 1, 2. There's your x values. And your y values, looks like we gotta scale this up to 7 at least. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Alright, so these points here. -2 and like a smidge greater than 0, so it's like right here. -1 and about a third-ish. 0, 1, 1, 2.7. It's right about here. And 2, 7 point something is like way up here. Okay. You guys see those points? Okay. So put it all together. I'll probably pull out Desmos in a few minutes. I could have put this into Desmos. It would have created the same curve anyway. Okay. Guys, this is a really classic curve. This is, of course, y equals e to the power x. Okay, you guys see that? Okay. Yeah.
How is the multiplied by 0, 1, and 7 to 0?
All right. So anything to the power of 0 is 1. Okay. Like as a rule. Right. It's like the power on something is how many times are you multiplying it by itself. So if you don't multiply it by itself at all, or another way is if you plug in, instead of whole numbers, what if I plug in like 1.5 or 0.5 or 0.3, 0.2, 0.1? As I converge closer and closer, this, and you can see this on the graph anyway, it's always going to approach 1. Right? That's true for all exponentials, with the exception of if you have 0 to the power 0. I don't think the calculator can do that. Let's see. Yeah, calculator blows up with 0 to 0. But anything else to the power 0, oops, is always 1. All right. So guys, look at this curve. Now this curve is really special in mathematics for, well, at least for this reason. You guys see if I hold my ruler flush to the curve? You guys see that? Could I get the slope like the rise of a run? Could you guys imagine there's a guy walking uphill and say, okay, that's not too hard to climb this mountain? And I say, okay, I mean, it's a little difficult. And it gets here, it's like, now I need like cliff climbing equipment. You guys see that? So the slope is increasing, the rise of a run. There's some rise of a run here. There's some rise of a run here, which is much steeper. There's some rise of a run here, which is fairly shallow. Okay, some rise of a run here. Okay. And it turns out, guys, you're ready for a crazy fact? Okay. It turns out that the slope of each one of these is exactly equal to the y coordinate. So the slope at the origin here is a 1-to-1 ratio. Right, rise of the run is 1-to-1. Here it's e to 1. Here it's e squared to 1. And here it's, well, about 0.37. Come on. Okay, you guys get that? Okay. Guys, this is the only curve in all of mathematics where the slope matches the y coordinate. So that's pretty cool. Okay. And another thing you can do with this is with continuous compounding. All right, so you guys remember compounding last week? There was like interest rates and the whole thing. All right, let's do this. Let's say the principal is let's say $1,000. I think we were using that last week. So you go to the bank, you put in $1,000. Guys, everybody taking notes? You go to the bank, you pop in $1,000. Okay. Let's say the interest rate is 5%. Okay. Now, guys, as a decimal for the calculator, what's the number you actually plug in the calculator for interest rate? Yeah, 0.05 for 5%. Okay. And let's say the time you leave this in the bank is like 20 years. Okay. Now, if you compound this annually versus continuously, you actually get different results from this. Okay, so let's look. Okay. So compounded annually, or compounded continuously. Okay. So annually, this is what we did last week. It's just A equals P times 1 plus R to the T. Just like that. Okay. So we're going to take $1,000 multiplied by 1.05. And we'll do that over and over 20 times for 20 years. Okay. Let's see how much money we get out of this. 1,000 times 1.05 to the 20. It turns out to be $2,653 and change. Like that. Okay. But you guys remember also you could compound monthly, where you could do R over N to the MT, and N could be 12, right? It actually came out to a little bit more money, right? But what if you compound not every year, like you're seeing here, not every month, not every day, not every sec, but like every single nanosecond, like continuously compounded? The formula actually looks different, takes a different shape, and it involves E. So we'll have the principal times E to the RT. Okay, because this really looks quite different from this. Okay? Like compounding annually looks like the interest rate is kind of in the base, but continuously it actually pops up in the exponent. That's weird, right? So let's say after 20 years, we'll take $1,000 principal from year zero, right, times e, that 2.718 character in the calculator, and then 0.05, and then we'll do 20. Okay. Notice I didn't have to add 1 to the interest rate like I did for annually. Right, so it continues to go like that. Okay. Okay. Do you guys think the answer is going to be? I'm going to guess maybe a 2,700, maybe something like that. It's going to be a little bit more than before. So 1,000, and then second e to the power of 0.05 times 20. Yeah, it is. It's $2,718 and then 28 cents. Oh, actually, you know what? That is I just realized. Wow. Okay, guys, we got some lucky numbers. What is 0.05 times 20? Blah 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 blah. 1. So e to the 1. So I just did 1,000 e, didn't I? Isn't that just 1,000 e? 1,000 e. It's a funny way to say that. Okay, there it is. All right, you guys good?
Yeah.
Okay. Okay. Now here, I want to do a little bonus question with you guys, which is, let's say you go to the bank and you're going to deposit some principal, and they say, oh, it's a 5% interest rate. You say, okay, 5%. You say, wait a minute, is that 5% annually or compounding continuously? You say, oh, actually, it's compounding continuously. Okay. So wouldn't the sort of effective annualized interest rate really be a little bit more than 5%? Right? Because they could have advertised maybe a slightly higher interest rate and just said annualized. Right? So that leads me to the next question: is what is a 5% interest rate? Let's say uh, interest rate compounded. Well, here, let me rephrase the question. Okay. What is the equivalent?
Can you go back
Yeah.
to the last page real quick?
This right here?
Yeah.
Okay. All right. So while you're writing this down, I'm going to remind you guys what's going on here. Okay. All right. So last week we were looking at this on the left side. Right, so if you compound annually, 5% just kicks in every maybe December 31st. Okay. Okay. So we're doing that for 20 years, 1.05 to the power 20 times the principal to get some money out of this. Okay. Now we also say compounded monthly last week. Right? So r divided by 12 to the power of 12t. Right? You can do that. Right? It came out to a little bit more money. Right? What if you compound like every nanosecond? Right? So now we got a new looking formula, e to the rt. Okay, you plug that in, and yeah, if you compound continuously, it does show up as a little bit more money than before. Okay, so now you guys all got this in your notes?
Yep.
Yeah, okay. Okay. So now the next question is going to be, what is the equivalent annualized interest rate for a 5% interest rate? Interest rate compounded continuously. There might be a few ways to find this, but I'll show you guys one method. Okay. So 5% compounding continuously. So as soon as I think compounding continuously, I know I can have this form, a equals p e to the rt. Okay. Now let's do this. Let's put in a principal of like $1 or 1 unit. I'll call it P1. Is that okay? Okay. Like $1, 1 unit, 1 whatever. Could be $1 million. Okay. E, of course, is E. Okay. Interest rate, I'm going to plug in 0.05. And T, I'll let go to 1. That's like 1 unit of time. It could be 1 year. Like 1 year. It's okay? Okay. And see, what do I get out of that? Okay. So what is e to the power of 0.05? And the answer is 1.05127. All right, and it goes on for a while, but I'll just cut it off there. Okay. Okay. So the target question is the equivalent annualized interest rate. So R annualized equals, okay. Like if you went back and instead of, let's say you go to the bank and they say, oh, 5% compounding continuously. They could have alternatively advertised an annual rate that would be equivalent to that. Okay? Okay. And who sees what it is? Guys, who sees what it is?
I see you.
What's the annualized interest rate? It's right here. 5.127%. Guess yet? Guess yet? Right. Because whatever unit of money you initially put in is going to grow by 5.127%. Yeah, right. So this annualized is equivalent to this continuous. It's the same thing.
When did
Okay.
Minecraft have
Is that-
time drops?
All right.
What does it do?
We'll do a couple other examples with you guys from the book. Right. So one is that they do talk about graphing. So let me show you guys a graphing example. So 5 equals 2e to the x. How do you solve that? So I can solve this graphing with Desmos. Bring this up here. Okay. So he said 5 equals 2e to the x. So I can say y equals 5, and then y equals 2 times e to the power of x. Now Desmos knows what e is, because it's a very special number of math. So I'll do that for you. See if I okay, there you go. It looks a little better. Okay. Okay, and the answer is just wherever the two curves cross. Because this is a graphical solution. You guys see that gray dot right there? The two curves cross? Okay. So of course the y value is 5. It was always going to be, right? But the x value is 0.916 about 0.916. Okay, so if you plug in 0.916 for x, then you get approximately 5 for y. Okay. Right, so you guys can solve graphically. You just type in the two graphs and set them equal to each other where they cross. All right, so you got that. And then also your book has some basic exponent type questions. Right, so here I'll do a couple of these with you guys. Okay. So how about number 2 right here? Because the highlighted ones I put on the main video anyway. So let's do number 2. E to the 4 times e to the negative 1. Okay. Guys, who can tell me what's this equal to? E to the 3. Yeah, exactly. So isn't the rule you can just add the exponents if you're multiplying together? And they have a common base, of course. Okay. Here's another way you could have said this. That's e times e times e times e. And then e to the negative 1, isn't that just divide by e? So that's that. That's another way to look at it. Okay. But the shortcut rule is you can add the exponents in this case. All right, let's do, how about number 6? Says negative 4 e to the 5x, and that's collectively squared. Okay. So I have two things multiplied in parentheses, and it's all being squared. So do each of these parts get squared?
Yeah.
Yeah. So the negative 4 gets squared, and then that's multiplied by e to the 5x, which also gets squared. Okay. Okay. So now we have a power to a power. That's different from the previous one we did, right? Where we're multiplying two numbers so you could add the exponents. That's not what this is. Yeah, multiply these exponents. Exactly. Right. And what about this negative 4 in front? Guys, what is negative 4 quantity squared?
16.
16! It's positive 16. Hey, did we just lose that negative sign? We sure did. If they never had a negative sign, we'd still get the exact same answer regardless. Ooh. Okay. So 16 times each of the, and what should I write? Yeah, there you go. 10x. Yeah, because you multiply the exponents 5x times 2 times. So that's the answer to that one. Okay. Okay, you guys see this? And that's pretty much a broad overview of every main type of question that's in that lesson. Okay. All right, so tomorrow I'll do 7-4 with you guys, Wednesday 7-5. Again, if you want to get a sneak preview, over the weekend I solved a bunch of puzzles from the book for the entire rest of Module 7. So I posted those to Classroom, so you could get a head start on those if you want. Otherwise, I kind of walk around and help you guys out.